Good afternoon, everyone, and welcome back. Today, I am again very excited to talk to you guys about another part of the polymer physics related to the polymer chain, polymer configuration, and polymer organization. So, again, before I start, I wish to show you guys what we talked about in the last class. And we will again do a recap about what we talked about in the last lecture. So you guys have a notebook and you can quickly look back and see what's going on, right? Pretty straightforward in the last class. We begin the class to talk about how does free rotation chain could resemble a polymer configuration, and that's the most ideal case. Right? So we begin the class, talk about chain model again. Begin with the model 1 is free joint chain model. This is the most classic model with very straightforward, easy to understand. In a nutshell, there's no restriction in any bond or any sort of thing. So you got a very flexible chain. And it's actually can sit on top of each other. So we go through the chain model and we use the class we did it in the very first lecture to talk about how does everything come into play using the vector concept to calculate what's the average chain, which is basically everything cancels each other. It will be 0, right? So we also use another concept to since this is not useful at all. So the first part of the last class, we really nailed the sum of the simple mass to understand how does this end-to-end distance would be equal to NL squared for this particular polymer, right? For free jointed chain. N would be how much bond you have. L would be how much each individual bond you have. I mean, what you want to take home message is this particular end-to-end distance would be N half L. So it's not a linear scale then to the degree, number of chain bond, right? So that's where the first part of the lecture, that's how we understand this part. And we chatted a little bit about a little bit more complicated way how to use metrics to understand the self-term versus non-self-term. And that's the beauty of this part. And in the second part of the class, since a little bit more complicated, right? So we used a little bit more sophisticated mathematics to understand another chain model, which is chain model 2. What is the second chain model? Anyone can help?
Free rotation.
Free rotation chain, correct. And in this case, now the bond between different chain has fixed angle. It can rotate, but it cannot flex between angles. Okay. Again, coming down to similar concepts. Well, we calculate for end-to-end distance. The mathematics is relatively simple. In the end, the process is a little bit painful to get there. But everyone follow me in the class, and we understand the end-to-end distance h will be what is it? NL squared dot cosine theta, or 1 plus cosine theta, 1 minus cosine theta. Right? So in this case, theta would be the bond angle. So we kind of run a little bit short of time in the last lecture to see how does everything physically meaning, right? We go through the math, we understand how we get there. Now let's talk a little bit about physics. How do you understand the difference between these two chain models, free joint chain and free rotation chain? So you want to compare these two? Let me use a different color to highlight them. First box is here. Second box is here. The difference is now you start to see it has one additional term. And let's take a closer look at this term. So what would be cosine theta be look like? If you have the bond angle, that's a typical bond angle is larger than 90 degrees, but less than 180 degrees. So this will be somewhere between 0 to 1. And as you see, this term will be larger than 1. And I actually did some calculation before I showed up in the class, and I want to show you guys how does this works out. So let me draw you a box that's very easy to understand. So this is going to be the bond angle. You will have bond angle in this axis. And in the upper term, we want to give this number. So this term we put there. So if you have perfect 90 degree, cosine theta will be 0, right? And it's kind of funny in this particular situation. If it's always fixed at 90 degree, this term will be exactly 1. Let's put 90 degree here. Okay, so if you have something bigger, 110 degree, if you do that calculation, I did it for you. If you use this term minus this is actually number 2. Okay, this would be the second number here. And you can continue to do this, you will see its exponential increase. Once something is closer to 180 degree, this value will skyrocket to almost infinity, right? But in real world, you won't have something that big. It's always somewhere between 120, which is 120 is roughly about number 3, and somewhere here. So in real world, this is a very likely you fall in a number somewhere between 3 to 10. This prefactor. Okay. So in other words, if you consider the bond angle, the difference they're going to exist between the free joint chain and free rotation chain. And this factor depends on specific bond angle. This value is somewhere between 3 to 10 is where you mostly will encounter in most of the flexible polymer. All right, so this then, if you put it back here, it's about a factor somewhere between 1.5 all the way to up to 3 times bigger than if without considering chain. So your chain is actually expanding while you consider this angle, okay? So conclusion 1. End-to-end distance will increase by roughly, let's give it, by considering the specific angle. Okay? So what else we can learn? Since once you think about a chain, if you fix the angle, if you know the angle of free rotation chain, now this would be a fixed number, right? And can we do something to it and understand it better? Indeed, quite a lot of physicists like to do. What they want to is pursue as simple system as possible. So instead of using rather complicated, this writing, they would do something very, very tricky but effective. What they do is that, why don't we name a new term? So that's what happened in the history, is they named a new term of this particular parameter. And this is something we will talk in the first part of the lecture. This is a new term. Let me put it here. Can someone help me? What would you name it? Segment? Chi? You definitely reading polymer physics textbook. Not here, okay? Chi is not here yet. What this factor do? This is a measurement of how rigid your chain, sort of, right? Because if you think about this, if this value is larger, which means the bond angle is more straight, so your chain is more expanded. And logically, you would say, let's just call it chain rigidity factor. So I would call it a physical meaning. Right? So this what you want to get it is how rigid your chain is using a number to quantify it. But in reality, it's not called this way. So it's slightly different, and I'll cover it. But that's a physical meaning I'm telling you. It's called chain rigidity factor. So they call it in the back? Ratio? Yes. If I'm telling you characteristic ratio, it's written as C infinity, and I'll explain what this term means. So infinity means this characteristic ratio works on when chain is infinitely long. And this is dependent on how long your chain is. This will change. So by default, people say, let's consider we have n is equals to very long, infinitely long. And C, they take this character. It's fairly straightforward, right? C infinity. But if you just throw it to any student, ask them what you would understand, what is characteristic ratio? There's no physical meaning encoded into this naming, right? If I would do it, I would call it chain rigidity factor. Please?
And that refers to the y-axis of the...
Right, yeah. So let me write down. C infinity actually will be equals to 1 plus cosine theta, 1 minus cosine theta, when chain is close to infinitely long. All right. So this characteristic ratio is defined. If it's defined, people use 3 dash line, means it's always defined that way. So characteristic ratio is defined as this term. And as you see, this we can basically write as C infinity here. They are the same term. This characteristic ratio, physical parameter, is the meaning of all these together, all these two, how it depends on the bond angle. And if theta is known, then C infinity is fixed, right? And we talked about that. So for most commodity polymer, from polyethylene, polystyrene, polypropylene, this C infinity is somewhere between 3 to 10. I'll give you a specific number and table in the later part of the class that you can get some understanding how this likely to be. Okay. So now we are sort of give it simplicity of the equation for free rotation chain. We're going to have a constant, which is c, and we're going to dot this, right? This will be a constant. And basically, you have a constant in front of the traditional term of free joint chain. And you will easily see the second conclusion you can get from free rotation chain is, this is a constant. So how does end-to-end distance depends on the molecular weight? Any answer?
I think the molecular weight is corresponding to the number of bonds.
Right.
The more bonds, the longer the length.
Right. So it scales the same way as free joint chain. In the free joint chain, end-to-end distance h is equals to NL squared. Or, this number is proportional to n root square, right? So you need to increase 100 times bond, then end-to-end distance increased 10 times. Okay? Same works for free rotation chain. The same model works here, that if you end-to-end distance need to double, your number of bonds still need to increase 4 times, right? It's still the root. You still have the root relationship here. So if we take a root, you still gonna have a root characteristic ratio dot n half and dot L, right? So what you learned from the first model still apply to second model, except free rotation chain somehow swells your coil or the chain model slightly a little bit bigger. Correct? That's the second conclusion we would learn from the two different models. Okay? As long as we consider this characteristic ratio, these two parameters are relatively similar model, except that this constant. And we will talk more in today's class and tomorrow's class about this specific term. Now you can see these two models, whatever you learn from most simplest model, free joint chain, you can actually apply to here with a little bit of correction. So this model is not totally wrong, but can give you some useful hint if you consider free rotation model. All right, so everyone is clear about these two very simple models we started off, FJC and FRC, not KFC. All right, good. So in the end of part, what we talk about last model is a little bit more complicated and hard to understand. Is what is the last model that can bring you one step more closer to reality chain? Is consider the bond, the rotation. Okay, consider stirring hinges, because in free rotation chain there is no energy barrier for the bond to rotate at different angle. So now I'm gonna give you again the same example I talked about last time. Think about this is a C carbon, right? So think about polymer polyethylene. So you're gonna have a hydrogen, and another polymer chain here, and you will have 3. You're gonna have 4 bond again for this carbon, and there's gonna be another hydrogen, and this is something gonna come out. And in this case, we will see if I consider rotation around this bond, so this particular carbon-carbon bond, which I would like to highlight as a green color. Now, you're going to rotate. Let's put it this way. Think about this. I'm holding an umbrella. But instead of, this is a broken umbrella being blown by a large windy day. So the umbrella is facing out. And at the end of the umbrella, there is a very big thing attached to it. Now I can start to rotate it, and you will see the steric hindrance is different. So when these two contact with each other, let's say in the phase where this bond is rotated up, then they will have more steric hindrance. So you will have a more energy barrier. So in this case, the last chain model, which we will not need to derive it because it will be very complicated, but we can throw out the answer to everyone, is called hinder rotation model. So in this case, we give it one more restriction. Not only in the theta angle between the bond is fixed, now you have even a preference in the angle. So we call this is theta, then we can call this rotation, which is perpendicular as a phi, for example. So this angle, phi, as you can see, it has a preference. Let's define, this angle between that one to be the phi angle. If I draw this way as a Mercedes-Benz symbol, so let's say you have a chain here. There's something in the back. There's another one. Then you're going to have two, right? As you see, if these are in phase with each other or 0 degree, this overlaps. If we rotate back, overlaps on the top of each other, it will have highest energy because steric hindrance. So if we think about this energy term, you will have highest energy, then you will have lowest where it's sitting sort of a little bit off angle. Then you have a minima, which is 180 degree. Okay, so this minima is minus 180, this plus 180. But in reality, because your bond is not that simple, there's a preference angle in this, is called phi, works out best for your chain. So if you consider this very complicated rotation model, what is important is this additional restraint. Theoretically, do you guys think it will increase how big the coil or reduce whatever coil compared to free rotation chain model? Any guess? Could be any. You have 50 chance to get it right. Either go up or go down. Think about now you have one additional restriction. Some brave student? All right. Since the last time we talked about FJC to FRC, it goes up. So it will be the similar rationale coming to that. Is now your chain is even more restricted in terms of rotation. So in that regard, this will give you out the same conclusion that it will has increase of the chain size overall.
So the restriction will make it more rigid. So
yes.
in the length.
It will increase end-to-end distance. Exactly, Nathan. So this comes down to another second factor comes into the first one. And I'll spell out this factor to you here. I'm going to use a little bit of space up here. So now end-to-end distance h square will equals to, again, NL square. It will also inherit the term you got from the first one is free rotation chain model, right? So you're still going to be 1 plus cosine 1 minus cosine theta. And it will multiply one more term. Is 1 plus cosine phi average and 1 minus cosine phi average. Because you think about energy rotation potential, phi will be a new term. Okay. So this is the same as this term. This additional restriction will increase your bond size. Is it clear to you guys? How does the three model relatively compare to each other? Free from FJC, FRC to HRC. And let's do a summary of how does each bond and restriction we have in this. And this would be a very useful table for you guys to understand what's the difference between three terms. So three chain model and different restrictions, right? So we have, let's write the different model, free JC, free RC, hinder the rotation model. So in this regards, I'll show you one interesting term is how does this works out. So in this, first is bond length. So in each case, the bond length is fixed no matter what model we talk about, right? So the bond length is always L, L, L in three cases. Now in the second case, well, the bond angle is now start to so in this case, you're still gonna no fix, so I'll leave it open. So this case it will fix as theta, and this case it will also fix as theta. Well, in this case, bond angle is free. Now the last is the bond hindrance angle. So that's a phi. So this will be free, and this will be free. And what matters for this is it's influence the final characteristic ratio for three different samples, for three different series, right? So in the first case, you're going to have characteristic ratio C infinity will equal to free joint chain model. As we know, it's basically as simple as number 1, because there's no characteristic ratio in the chain, or these two terms are basically free so that they will average out each other. How about the second term for free rotation chain? In this case, now you have a theta angle come into play, right? So this will be come into play here, where we have actually written here, where you start to have a term right? Now characteristic ratio is equal to this value. And we chatted a little bit about how this would influence your chain length, because this will be somewhere between 3 to 10. And I will discuss a little bit more after the break. And if we consider this bond angle, we're going to have two restrictions coming from the rotation angle and coming from the bond hindrance. And is it clear to you guys how does theta and phi relatively works out in the bond? What I mean by theta and what I mean by phi in the chain model? Okay, great.
So the hindrance correction, that is a correction to the rigidity factor. It's not like its own new factor.
Yeah. So chain rigidity factor, let me be clear on that. Rigidity factor, or don't call it please. It's called officially characteristic ratio. So the characteristic ratio is related to everything before NL square. Okay? So anything before that we call it characteristic ratio. So basically I write it here, characteristic ratio will be equal to 1 if it's NL square, right? Because effectively that would be 1. Characteristic ratio would be 1 plus cosine theta, 1 minus cosine theta if you consider the angle. And in the last case, if we consider even the hindrance angle, then there's one more restriction here, and that's being reflected. Okay, a question in the back?
I don't understand what angle phi is.
Sure. Relatively easy to understand. So I wish I have an umbrella. If I don't have it, I'll use again my arm. Think about this. My arm was this bone. This particular one extended out. Okay? So theta is the angle where I can reflect in this way. It's changing the angle between, this straight bone to this. If I go straight, theta will be 180. If I bend, this will be 90, right? Phi is the angle 90 degree perpendicular to you. Phi talks about how you can rotate. This angle is not changed, but phi changes now. And phi 0 means is I have the one arm, in phase with this one or parallel to that one. So if I'm sticking my head in the board and I look that direction instead of look this way, right? I'm now looking 90 degree. Now I can see how two discs play. They can rotate relative to each other because this bond is rotatable. It's not bendable, but it's rotatable.
So is it taking into account steric effects? Is that kind of what
Yeah, yeah. Because in this way, this bond is not related to steric, but this bond will relate to steric. There's one question in the back.
If all your hydrogens are overlapping, is that 0 or 180?
If everything is overlapping, that will be 0 degree, where the energy is highest. Let me give a crazy example. If I lying on the floor straight, now I have, think about my leg is one of the bond, my two hand is another bond, so I can now got center is my chest, right? I got one bond, another one. So somehow in the future there's a magic technology can replicate me. Then there's another me standing in front of me, okay? So this is a showdown A, this will be showdown B. Both doing this. If they both stand up, their leg will overlap each other, and this will be the highest energy. And I won't do a flip over and stand on my hands, but if I do that way, my leg is now 180 degree versus each other, where I have less chance that my leg is hitting each other and reduce the energy. Okay, now I can do this. Rotate. That's basically the angle coming into this phi, the phi angle. Okay? And as you can see, the lowest of the energy will be 180. And if you rotate a little bit, there will be another local minima, which is I draw it here. All right. So, any of you?
Realistically, we'll have an angle for theta between 90 and 120 degrees. So you said our first conclusion was that it would increase the distance by 1.5 to 3 times.
Right.
For c theta, or c infinity.
Yeah.
Next to on your table, you wrote about 3 to 10 times.
Uh-huh. So that will depend on real bond. So in this case, think about the case that you're not like a very simple carbon-carbon bond all the way. Now you have something hanging out as polystyrene, for example. The backbone is still, carbon-carbon bond, but you have dangling group coming out. These will come into play how it affects in this characteristic ratio. So Well, at the beginning of the next class, I'll demonstrate a few examples how different real polymer, that any polymer you would be used polystyrene, polypropylene, you use in your daily life, and what is characteristic ratio they will be at. Okay? So for this first part, the question?
For these models to be true, do you have to assume it's a homopolymer?
Yes. So not only it needs to be the homopolymer, where in this case, we just assume it will be the simplest case. It will be the backbone with just all the carbon-carbon bond. But in real world, you will see the backbone could have heteroatoms. It will influence characteristic ratio. And we will not talk about this class, but in the next class, on this Thursday, we will talk a little bit about worn-like chain model. In that case, you will have, for example, if you have a fused ring, like a sulfene unit or a benzene unit in the backbone, that typically encountered in other rigid-like chain model, that you need a different model to describe it. Because in this case, we assume there's always a bond angle, and bond angle can rotate. But if you have a fused ring, it's super rigid and rod-like. And the current model does not describe it. And good question. Any more questions before we move up? Because those are the foundations for what we're going to talk about in the next 3-4 lectures. Those 3 different chain models. What is fixed, what is not fixed, and what is this C infinity, or known as characteristic ratio, is coming into play. Or also known as how rigid your chain is. If not, we can take a short break, then take a 5 minutes break while you guys digest a little bit about these 3 chain models, and we will move on to talk about chapter 6.3. Okay?
Did you get a chance to look at? Oh, I'm sorry, I was talking to.
Mm-hmm.
Did you get a chance to see the presentation?
Yeah.
I just want to show you, this is how I was taught to draw those.
Yeah.
Thought it might be helpful to you.
Yeah.
'Cause it makes it really simple
Yeah.
to see.
Yeah, indeed.
Mm-hmm.
I think this is very good. I like this. And indeed, this is what roughly the energy would cost to rotate, right?
Yeah, I forget what these projections are called, but some chemist,
Yeah,
some
they
famous guy started.
yeah, they has a term for this particular. All right. So I'm gonna get clean up a little bit and get ready for the second half. You have a particular question?
What is the typical characteristic ratio for this term? So that one's 3 to 10.
So
this entire term is like.
So actually, I would be more straight. So this is 3 to 10, not this.
Oh, okay.
So this will come into a little bit of difference in the real value, but in the end, it's this 3 to 10.
Okay.
Yeah.
Okay.
So I give you this number because I want to give you some real idea how big they would look like.
Okay. Yeah.
Because otherwise, it's a physical term, but you don't know how big or how small. You know, is it 100 or 10 or 5 or 1?
Yeah. Okay.
Yeah.
Sweet. Thanks.
Do you want to practice tomorrow night, I guess?
Yeah, that'd be good.
Okay.
That'd be good. We can probably do it in here, even like sort of like connecting everything and all that.
Right.
Okay. Dr. Gear,
Mm-hmm.
do you speak any other languages?
Yeah, Chinese.
You speak the Mandarin?
Yeah.
How long did it take to learn English?
I not consider myself to be a good speaker, so I actually learned quite long, maybe even 5 to 10 years. We started in the age of 8 in my hometown to teach that. Yeah, but I still found not very good. But if you want to learn Chinese, probably a couple hours. I would say a couple hours a week would get you up to communicating, talk, and listen without problem.
You said a couple weeks?
and a couple hours a week.
Oh, okay.
Yeah, but if you want to write and read, that's typically harder.
Yeah.
You're speaking about actually how we're gonna handle our kids, because he is likely not gonna be able to speak Chinese. He will understand, but maybe a little bit speaking.
Yeah.
I don't think he can still
Yeah,
do read
'cause
and write.
my goal is to be able to at least communicate proficiently in Spanish, German, and eventually Mandarin.
I would say the last may be the most difficult, because it's a
Yeah.
different language. The grammar is different.
Dr. Story's gonna love those. We have them. We will.
I figured it would.
He has peppermint patties in his office.
Is it actually functioning?
So it's a good
Okay.
place.
Tired. Humidity just like.
When we're back, we get like Jolly Ranchers. So it's like a step up, definitely.
Like my master going.
Yeah.
Do you need something?
I don't know.
Seeing if those workouts were actually working. Just
Dump you out of your chair. Or to parkour and make sure, like, to, drag my ass across the back of your head.
just do a flip and land in the chair.
Then you don't want to break your elbow again.
Yeah.
A lot of kids have switched sides because there were some people that were on that list that like weren't.
Super cup I totally stuck in my head.
There was one, yeah.
Which John?
A meme.
Am I missing one?
Everyone was there.
I asked him about it, he said, that's fine, just go ahead and like, church after class.
Oh, I don't have to be there for it. Okay. Because it's our class.
Spotify playlist called Spotify Lecture, right? It's totally by Africa over and over again.
That's perfect. So what, you first shuffle to see what it'll
Dr. Bill, did you just get that? The microphone?
Yeah, for you guys.
Amazon or?
It's a very specialized company. They sell all the audio equipment. Yeah, it's called a BH camera.
Nice.
Yeah.
You two have cool electronics.
Huh?
I think you guys are the two with the coolest
Me and
Yeah,
Yo.
'cause you have the Surface and the pen, and you have
He has
you
a.
have this, so.
I totally got this for the class. So actually, I only put this in my office and charge it.
It's good for family photos.
Especially for y'all.
Yeah. Yeah. Okay, let's wait a little bit for the last student, then let's resume to talk about. So, chit-chat a little bit for these three models. It's very important to understand first two, and this is a little bit abstract. Although, you got this a little bit more closer to the reality of the chain. Well, let's say you shoot the arrow. You have a target. This was quite off. This may be not even on target. This is a kind of already close. This improved a little bit, but not necessary. Sometimes for the very beginning class, if you consider this model, it's sometimes more confusing for you to gain the benefit of additional accuracy. But if you're a polymer physicist, then this would be the beginning of your journey to most precise predicting the chain model. Because apparently, we didn't consider heteroidons as we covered in the last part of the lecture. We didn't cover the different bond lengths, and you need to consider everything to really predict a real chain model. So I'm gonna give a little bit spoiler to Young Simon's class. There's techniques that you can measure end-to-end distance. It's not just an abstract term, but you can measure it. and you can understand how big or how small it is. And it's a very interesting technique called the scattering, and everything starts to get strange while you're in the scattering mode because everything is start to inverse. You need to consider it differently. But I will leave that to Yom to talk about in the next semester. But you can actually measure end-to-end distance using characterization technique, and you can compare with what theory predicted and what you measured. Okay. For the second part of the class, I'm going to talk a little bit not so abstract, is something related to what you can see and what you can understand is some of the polymer and how we can use that to understand our system. So in this case, we're going to start to talk about a few polymers. I'm going to write it on here. So for PEO, this value is somewhere about 5.6. You don't need to write down. It's actually in the textbooks. You can actually look it up. There's a table tabulated, very nice for you. So as you can see, this is roughly somewhere between 3 to 9. And I'll pick some more examples. So for the PDMS, it's slightly bigger, as you might expect. There's a little bit more in the side chain element. So PMMA is one with sample on the more rigid side. So this characteristic ratio is somewhere close to 9.0. All right, and polystyrene is the one, and we use a lot in our lab. It's another commonly used glossy polymer. So these values will help you to roughly ballpark how you would count, how you would get the molecular weight, and how you would estimate what's the end-to-end distance for your material, or how big the coil is in the real world, right? Because you can physically measure the molecular weight. If you know the molecular weight of a polymer, you can inverse what degree of polymerization that can be come down to n, and you can calculate what is carbon-carbon bond to know end-to-end distance, right? H. This will be n, right? So you can really do some very simple characterization. It matters in quite a lot of application. I'm gonna again talk a little bit. Spoiler is it's sort of less important in the solid states. It's more important in the solution states. Once you want to consider if one coil would be overlapped with another, you can estimate how big the coil is, what would be the overlapping concentration if you assume these are packed as one sphere over each other. These would be useful for this technique to look at characteristic ratio. All right, so any question for this part, how these character ratio value are and how they can be potentially useful for you guys? All right, so now I'm gonna then move on to the next part where I talk about characteristic ratio, and is there any way we can still go back to this model? And is there any interchangeable way we can play, or magic we can play, to come back to free joint chain model? I'm obsessed with this model because I don't worry about anything. I just need to know what's the N and L. I can get all the parameters I needed. And a lot of times this is beneficial. If you have NL, that's all you need to know, right? So I did not invent this. There's other group that invent this way. Is why don't we hypothetically think about another coil? Let's think about two coils, okay? So let's call it a case A, where you have a chain, but there is a free rotation chain model. So the end-to-end distance will be, square will be, and C infinity and L square. Is there a possible way you can make it equals to another model that is free joint chain that shares the same physical size but with different chain segment? Now I'm gonna draw a little bit differently, but you got the idea. The size will be the same, but now we use a different model to describe it. So in other words, HL square will be the same, but now you're going to have a new definition of MB squared. So if you read this, this is describing as free joint chain model for the end-to-end distance. In these two, n, if you think about it, it's a new term. This will not totally equal to this n, because it's basically a different n, right? So you define a new n, you define a new b, that if you put a closed in the box, you don't see what's going on behind the box, they will behave exactly the same. Why we need to do this? As I said, if we do the second way, we hypothetically think it's a new chain, then we can simplify the model. We can eliminate this C infinity term, right? And you will actually encounter it a couple times throughout this course. This hypothetically free joint chain will show up throughout the lecture and how they would affect your chain model, okay? And this particular thing, we can actually calculate what the B is. And people have given the different definition. You can actually use n defined as if you use degree of polymerization. And then these are n is number of bonds is slightly different between these two, right? Because degree of polymerization is what in this box. So this is degree of polymerization here. And bond is how much, if in this particular box there's, for example, polyethylene, you have 2 carbon bonds per box, then n would be equals to multiplied by n. So if we define this as degree of polymerization, then we can define this called monomer length. So in this case, this B is not going to be a real term that directly linked to carbon-carbon bond length, but it's idealized what each segment will look like in your bond. Okay? So if you do this way, not bond length, segment. So in this case, now B is something that we don't know, because these two are the same. If you know this, you can calculate what H, and you know the N, you can back calculate the B, right? So B will be a hypothetical term. It will be slightly bigger than carbon-carbon bond, but it will be something relevant to the physical size of your polymer. If you know this, and you can even ask the elementary school kids, they can do a very simple math here, NB squared. So in other words, so this is a recipe for simplest understanding of chain configuration. Let's say you have a polyethylene. Again, I like to use this as the beginning of the class. So you will know, in this case, N is equal to 10,000, right? That's how much dp is, degree of polymerization. Well, how you can calculate the end-to-end distance is have two ways. Method one. A lot of people use is you can calculate what is n equals to twice of that number. Right? You know this. And you can look up characteristic ratio, which is, I didn't list there. I have to look up in the textbook. But let's say this is somewhere between 6. Okay? So you can calculate end-to-end distance. H will be equal to 6 root multiplied by n, which is again then multiplied by a bond length, right? 1.5 angstrom, and you can calculate how big the end-to-end distance. This is one way you can get it. And this is where we talked in the first part of the lecture. H equals to root c infinity, or characteristic ratio, root of n multiplied by L, right? That you can know the end-to-end distance. That we call it method 1. And there is a method 2. It may be a little bit redundancy, but now you can also calculate H equals to n, which is shown right here. By multiplied by B. B, you can look it up. Actually, B has been discussed extensively in the literature, how big this segment length for this repeating segment, okay? So you can look it up. I'll write down some of the value for B for you. So these two are interlinked. So B for individual one, for PEO, that's about 6.0 angstrom. So that's about 4 times bigger than a typical carbon-carbon bond, right? Because you think this way, PEO has the structure of I'm missing a C. Okay, so theoretically, you would expect 1 bond, 2 bond, 3. CO bond is slightly longer. But if you add everything straight, this will be somewhere close to 4.5 angstrom. But since we use hypothetically B, it's considering this infinity or characteristic ratio. You can directly use this to calculate. MB squared would be easier to use. And I'll give you a few more examples. So PDMS has 5.8. PMMA has 6.5. And polystyrene has 6.7 angstrom. So beauty of this, you don't need to consider bond angle. Characteristic ratio has been rolled into this term. All you need is to calculate the degree of polymerization n, and you can use MB squared to understand that.
So you can just look up N and B and the C to infinity term for any polymer.
Yeah,
there's. Is it like temperature dependent, or like other conditions, or is it just one number for one polymer?
This is a very, very good question. So let me discuss each individual terms you asked. So temperature, as well as what else?
I just said conditions.
Yeah.
I don't know, like solvent.
Yeah, solvent will affect. So especially the solvent is one of the most critical thing, as I discussed in the first lecture. How if you polymer in a good solvent and a bad solvent, it will matters how expanded your chain is. And I will talk just a little bit, touch base with that part. So the other part, characteristic ratio, has one very, very important assumption is it will have relatively high molecular weight or degree of permeation. Because in the last lecture, in the very last part while we eat in that very hard to chew entry, we omitted a second term in that expansion. And that omission was under the assumption that n will be very large. So 1 divided by n will be relatively small versus the other term, right? So C infinity works out if your chain is high enough, the molecule is high enough. Actually, in the textbook, we also discuss how C infinity depends on how long the bond are. So let's say characteristic ratio will depend on n, or how degree of permeation. So EC infinity is not an inherent property. It needs to be used at infinity. If we remove the infinity, it's called C, or just characteristic ratio. And if we plot bond n is how many bonds along the polymer chain. If the n is large, it means it's long polymer chain. N is small, it's the short polymer chain. Let's give you the extreme. So if it's 1, it's just one bond. Then you will see C1 is basically doesn't relate to anything, right? If it's one bond, it's always going to be flexible or free joint chain, right? If it's just one carbon to another carbon, even the bond doesn't make sense, right? So it's going to start here, and now you have 2 bonds, 3 bonds, and as it goes on, this will increase. And it will reach a value and plateau out at infinity. We call it C infinity, a characteristic ratio. As you see, this guy depends on how long your chain is. Or otherwise, your end-to-end distance will depend on if your degree of polymerization is short chain or long chain. But lucky enough, let me finish this. Lucky enough, most of the polymer, this is so close after n equals to 100. So in other words, most of the polymer we handle today will be very close to the C infinity you would get theoretically. Okay? So a short answer to you, yes, C infinity depends on the molecular weight. But lucky enough, while we're working on the polymer, it's always in the region that it will not depend on the molecular weight if your molecular weight is relatively high when n is larger than 100. So coming back to the second question, he is asking about how does solvent affect all we talked about here. I'm going to be surprised you say everything we talk about is we talk about a polymer chain in the vacuum. There's nothing around it. So it's just a chain, then empty things around it. And there's no gravity and nothing, so it's not a real world. What we talk about here is just a model works on your computer. But don't be discouraged for now. Still useful to study them. There's several lucky cases that your polymer property will be related to what we talked about here. And these are very specialized conditions. There's 2 cases that your chain will behave like, remember the word, behave like free joint chain. 2 cases. I want to ask you, when would that be? These 2 cases, your chain behave like free joint chain. If really physical polymer that can overlap each other, or
2-membered ring.
Hmm?
Really, really small.
Really small. Well, that will that meet the same condition as free joint chain? Maybe you can elaborate a little bit more.
Like, if it's only 3 of them,
Yeah.
then perhaps with like free jointed chain.
You mean 3 bond?
Yeah. So.
What about at really high temperatures?
Right.
Really good solvent.
Oh.
Close.
You can
Close.
never get free joint chain because you can never have 2 atoms in the same place.
Right.
rotating.
Right.
But you
But-
can do free rotation chain if you give it so much energy that the hindrance doesn't have as much effect.
Right. I mean, it's close enough to what you say. Still, there's a slight difference. So, let me explain 2 different cases. They would never behave like free joint chain in real case because, I mean, it's just the anti-physics that your 2 bond can sit in the same position. What we mean here, use free joint chain to describe these 2 cases, is end-to-end distance, what you get measured experimentally, agrees with NL square. Let's first be clear about that. And so, if the results matches or your chain is happen to be that big, we call it a special condition. And there's 2. The first thing I want to talk about is related to solvent. So number 1 is, it's a very weird thing again. Blame the polymer physics is why they call that. It's called theta solvent. Or it's again a very interesting term, a little bit tongue twisting and not very self-explanatory, but it basically says theta solvent is defined to be a solvent condition that your chain size will behave like free joint chain. Okay, and I forgot who mentioned that. Is it the good solvent? Actually, it's not a good solvent, surprisingly. Because a good solvent, well, you fully dissolve the chain, think about what's going to be happening. They will expand, right? As I described, there is no physics where two bonds can occupy the same space. So, in a very good solvent, your chain is more behaved like here in hinder rotation model, or even more sophisticated model that models your chain. In one another, so let's call it a good solvent, right? So that will be something close to this region. And as we talk about, if you go in from top to bottom, our chain expand. Well, we consider 1 prefactor or 2 or 3, your characteristic ratio will increase end-to-end distance by a factor of somewhere between 2 to 3. All right, how about the other extreme? Somewhere even higher than that. It's collapse. Everything is very tiny. It's in a bad solvent that you will be much smaller. Remember the first class we talked about 2 cases in the Gaussian chain. Your polymer chain is somewhere closer to in fully extended chain is somewhere closer to a football field. Well, it's fully compact. It's like a baseball. In real chain, somewhere between. Okay, so if you keep adding bad solvent to your polymer, there will be a time your polymer will start to shrink little by little, right? Because it's bad solvent and don't want to expand. It will pass this point in terms of coil size, right? Then we stop there. We call it theta solvent condition. So in a nutshell, theta solvent is not a good solvent, but neither a bad solvent. It is just a solvent makes a chain behave like okay, so please mind the words. So make the chain behave like free joint chain. Free joint chain never exists, but you can sort of find a niche condition that your chain coil size is as good as a free joint chain. Okay? And the second term is two cases. The second case is a little bit hard to understand. It's relatively abstract. The second condition is we're in a polymer melt. So in this case, a chain is melted. It's floating by all the chain around itself. Actually, in this particular case, your interaction between the neighboring chain will cancel out each other. The effect of expanding, it will behave like free joint chain. Very, very surprising, but that's basically what people observed. So in the melt, a polymer chain behaves like free joint chain. So, although it's a little bit, a lot of you may be doubting why we start free joint chain. It doesn't seem realistic, but in real world, it matters in several important cases where in the Seda solvent as well as polymer melt. Okay? So is it clear for what is Seda solvent and when does this free joint chain actually can be observed in real world? And this is actually more closer to good solvent when your chain, please?
You said that during polymer melt, the interactions cancel each other out.
Yeah.
Okay.
So the neighboring chain actually cancels out the expansion force of itself. That's why it's showing or behaves like a free joint chain. Or this would be the words I would be using. Okay? I want to use this opportunity again to talk a little bit about what would be in the good solvent will behave like. In the good solvent, since everything will come into play, your chain is actually will be even bigger than this particular term. So in all these three terms, there's one common relationship between how the end-to-end distance depend on the number of bonds, right, or degree of polymerization, and root square multiplied by L. So if you watch carefully, this is basically a constant. Well, we talked at the beginning of the class. Now, its value is fixed. Bond length, if you know, its value is fixed. So what it only changes is n. And how does these relate to each other? We can basically write h is proportional to n power of half. Right? So that means whenever n doubles, h only increases by a factor of 0.5. So this a new term is called proportional. And as we say, this would be in Seda solvent, right? So in good solvent,
What do you mean by good solvent?
in good solvent, which means it's a super soluble.
Okay.
So the chain is fully dissolved in that case. In the bad solvent, it will be collapsed down into a globular.
So theta solvent might be partially solvent?
Yeah, exactly. That's the point. Well, we talk about there. It's sort of somewhere close to the good solvent, but not as good as the good solvent. That's why I say, if asked me to name the name, I don't know how to call it. Probably Seda solvent wasn't too bad. Good but not so good solvent? Yeah, it's too tongue twisting for this Seda solvent. So in good solvent, how does these link to each other? So again, as I mentioned, so in this case, good solvent, your chain will be bigger than that. In this particular case, how does these relate to each other? I want to use this again, the proportional term. So the h will be proportional to actually n of 2/3. And we will talk a little bit later part in this lecture how we get this. Sorry, this would be small n. So how does these works out each other? So you can see for the same polymer, if it's in a good solvent, well, you increase n, the end-to-end distance increases much faster. This scale is about 0.66. Well, this scale is n 0.5, right? And this is one of the characteristic about good solvent versus bad solvent. And whenever we talk of solvent, we kind of quite different with what we talk about here. This you should think about, it's isolated chain, lives in a computer that lives in a vacuum. We don't consider any bond interaction. We should only consider it's a rod that can rotate or not. Okay? We will get closer and closer to the reality. How does solvent come into play? Okay? So for this particular lecture, we basically discussed in more depth about these 3 different chain models, and we defined a few new terms. One is called the characteristic ratio, which I just erased here, which how we can use this as think about how rigid your chain, because that's basically what the physical meaning is. The higher the characteristic ratio, your chain will be more rigid, and it will be extending or expanding to end-to-end distance. We talked a little bit about the real world, how does these value will look like for these characteristic ratio. I mean, somewhere you want to memorize sort of, it's somewhere between less than 10 for most of the polymer. Of course, there's super rigid polymer will go above 10, but most of commodity polymer, they're sort of semi-flexible. You can use C infinity to describe it, or if you can use an equally important term is, they call it roughly a segment length, where you can calculate what the B is and use degree of permeation MB squared to count how long your chain or how big it is. All right? So with that, I think we can summarize today's lecture. We introduced a new term, and we went a little bit deeper in terms of concepts. The good part about today is we didn't go through any much more equations. I like take an on day and off day to go through a more complicated equation. Today is more about what's the physical term meaning of characteristic ratio. If you want to leave this class, please remember what this term C infinity is. And with that, we will come back to the next class. So next chapter, we will move on again in the book. So if you haven't read the textbook, please read it at least once to understand what the chapter 2 different chain model is. So for the next chapter, we will introduce what is a few new terms or jargons for the polymer physics. What is a Coulomb length? What is persistence length? What is one-like chain model is in the next class. And why we need to study that is, in this case, we assume it's sort of simple carbon-carbon bond. But in a lot of real world, a lot of polymer are not behaving like that. For example, the Kevlar, which you use in the armor or protective vest, they are made of aromatic backbones to make them super rigid, and these bonds are translated into better mechanical property. Same for other material. I can give you an example is DNA molecules. They're also relatively rigid because of backbone structure. And with that, we can resume in the next class to talk about rigid rod like a polymer. Okay? KFC model. You want to start it?